Okay, here to continue with the carbohydrate discussion. Let me get in here. So up to this point, we have discussed the monosaccharides, your glucose, diabetes, all that mess. We talk about then the dehydration synthesis event that can connect two of the disaccharides together. We're going to look today now to finish up this discussion on oligosaccharides and the polysaccharides. So these are the last two categories. I'm going to jump from disaccharides to polysaccharides. And I'll come back and address the oligosaccharides at the end. Right? So let me get through all of this here. So again, the fourth structural category, I'm skipping the third for now. The fourth structural polysaccharide or fourth structural carbohydrate level being the polysaccharides. So polysaccharides are nothing more than just giant molecules made up of those hexagon-shaped monosaccharides here, held together by glycosidic linkages, that covalent bond that holds one glucose to another glucose, or a glucose to a fructose. So it's just very repetitive. And I think you have heard of two of these types of polysaccharides. One is what we call amylose. We know that as starch. They just call it starch. The technical name is amylose. And then my other one, I don't know why it's skewed over, but the second one, we'll just call it glycogen, right? Glycogen is basically a type of animal starch. So we find that in human, in animal types of systems, starch, amylose in plant systems. These are associated with energy. Right? When we think about polysaccharides, you're thinking about energetics, energy. So molecularly, they're similar, right? They're made up of these little monosaccharides. Starch is a little bit different shape, not by much, right? It's just glycogen's a little bit more repetitive in its nature, but they're both very similar. They're both high energy molecules. Amylose or starch for plants. You may have heard of like vegetable starch, corn starch. That's the energy molecule for plants. Glycogen is the energy storage molecule, the energy carbohydrate storage molecule for humans. So if you were to go out this evening and eat a baked potato, you know, you're getting a bunch of other vitamins and nutrients, but you're getting a very high amount of glucose, right? But we don't say you're just getting a bunch of glucose. You're getting this big aggregation of starch, right? So every one of these little molecules is glucose. So let's say we have grandpa that's diabetic, and the doctor tells grandpa, no more tortillas, right? No more, breads, no more baked potatoes, that kind of stuff, no pasta. And grandpa's confused. He's, well, tortillas are not like candy. Why can I not have tortillas? Well, tortillas contain a lot of starch, right? Breads, baked potatoes contain a lot of starch. And what happens when this big molecule hits the digestive system? All of the little monosaccharides, the little hexagon shapes, will be broken off. And we see a huge increase, a huge spike in blood glucose levels. If grandpa's diabetic, can't control that glucose, then he's going to have a huge spike in his blood glucose, and again, runs the risk of being hyperglycemic, things like that. So again, it's that correlation. No, it's not sweet like a candy bar, but it contains a tremendous amount of individual glucose molecules. Right? Same thing for meat products. If you eat meat, you're going to get fats, you're going to get amino acids and proteins, but you're also going to get any stored glycogen that was in that meat. Right? So our muscles are very active. Right? We have to store our fuel where the fuel is going to be required and where that fuel is going to be easily accessible, and that's within the muscle cells. So muscle cells have lots of space that is there available for glycogen to fill. Now, this has relevance if you participate in athletics. Let's say that we're going to play soccer. We're going to go on a 5K race, a big, long cycling trip, or a big, long hiking trip, something like that. So we may want to consider carbohydrate loading. So what carb loading is, it's the purposeful consumption of carbs to maximize glycogen supply. So we're on purpose. We're eating a lot of carbohydrates, a lot of pastas, a lot of tortillas, cereal, pancakes, breads, a lot of pasta to maximize the amount of glycogen we have stored in those muscles. So think of your muscle cells kind of like a gas tank, right? Do we have enough energy to sustain our activity, or are we on empty it's not going to sustain our activity? So we want to be over here and not over here on the empty side. So let's say, I don't know, little Susie's got a competitive soccer game on Saturday morning, right? So let's say like on Wednesday, we address the physicality, we address the actual technique, we do conditioning. Most coaches are okay with the technique and the training part. Most coaches overlook the diet and then the nutrition part, right? So you can have the most awesome athlete, but if they have no energy, they're not going to perform well, right? So they got to go hand in hand. But let's say, so Saturday's the event. So on Wednesday, about Wednesday-ish, we start pumping little Susie with a lot of carbohydrates, right? So waffles, pancakes for breakfast, spaghetti for lunch, workout, but again, try to replenish these. By Thursday, the workouts should start to get a little bit less. By Friday, very minimal workout and a lot of carbohydrate consumption. So hopefully we will have moved little Susie's glycogen supply up here to the full level. Now, we term this as short-term energy. So let's say you or little Susie or somebody has their cells maximized out. They're completely full of glycogen. What does that translate to in terms of time? How long can Susie now sustain her activity with a full carbohydrate, a full glycogen supply? Well, it's actually not going to be that terribly long, right? It's going to be somewhere in the realm of about 15 to about 20 minutes. So when we talk about carbohydrate loading, we're talking about sustained consumption, purposeful consumption of carbs, which translates to sustained aerobic activity. So this is running that 5K race, right? We're not stopping, taking breaks. We're swimming consistently. We are cycling consistently, right? And these endurance type of events, like soccer, when you play soccer, run back and forth, back and forth. You get hurt, that's okay. They're just going to roll you off and put somebody else in, and they're going to continue running back and forth. There's not a lot of standing and just watching, right? Like American football is quite different. It's a lot of standing, a lot of just down, they get tackled, and they walk back to the huddle. So that you wouldn't really, or I should say carbohydrate loading isn't really designed for like football. Carbohydrate loading is more designed for endurance activity, basketball, swimming, soccer, those types of events, running, right? So, and 20 minutes of sustained activity is a fair amount. I don't know if you have a treadmill at home or you want to go jog around the block. You jog for a while and you think, man, I'm already getting tired. And you look down and you've only been jogging for like 2 minutes, right? Well, this will fuel sustained high intensity aerobic activity for about 20 minutes, right? This carbohydrate loading. If you've ran a 5K, you ran a 10K, maybe a marathon, as you start to deplete, let's say we're depleting our carb energy at about 20 minutes, you are going to feel fatigued. And a lot of people want to stop at that moment. No, I can't run. I gotta stop at this point. I encourage you to keep running beyond that fatigue point, because once we shift to zero, once we're out of carbohydrate energy, the body has to find energy somewhere else, and it shifts now into the fats, into lipid energy. And you'll feel that little surge. You get that, that little, I've heard it called a runner's high, right? The runner hits the wall, they keep running a little bit more, and they get that surge of energy, right? That's because our body taps into a new type of energy source. That's the lipids. So we have a lot of lipids to burn. Yeah, lipids will sustain you for hours and hours and hours, days. But carbs only a very short 20 minutes. So now, to put this in a different perspective, let's say that you're not trying to carbohydrate load, but you do it accidentally. Especially now, during the sort of this time when, during the quarantine that passed, or during this time where we're not quite back to normal, functionality, working out, that kind of stuff. A lot of people will sit down and watch a movie at home, or they go to the movies when they're open. We eat popcorn, or maybe we would a dinner and a movie, right? You go and dinner, ooh, nice dinner. Let's go to the Olive Garden and eat pasta, right? We got all these carbohydrates, get dessert. We go to the movies, we get more carbohydrates. At the end of the evening, there's a chance that maybe the date went very well, and there's a chance that we might burn some calories. But no, it didn't happen. No, it was a nice evening. Good night, yeah? So that didn't happen. We didn't burn those calories. And what happened? We start to work build our glycogen supply. So let's say the next day we go to the gym, we go work out. We work out for 20 minutes, right? And we think we do a good job. Man, I work out for 20 minutes. But what if I worked out for 20 hard minutes and I had 20 minutes worth of carbohydrate energy? How much fat did I burn? It's going to be a sad answer. How much fat did I burn if I worked out for 20 minutes and I had 20 minutes worth of glycogen carbohydrate energy? I burned 0 grams of fat. Right? It's going to tell me you burned this many calories. Oh, that's nice, right? I burned all these calories, but all those calories came from carbohydrates, from glycogen, and not fat. So keep this in mind. If you're trying to, most people go to the gym to work out to lose weight, or to get strength, or to feel good, whatever. But if you're trying to go to the gym to lose weight, be conscious of your carb loading. Right? You may want to kind of reduce the amount of carbohydrates you're taking. So let's say we're at half, and let's say we have 10 minutes of carbohydrate loading. So when you go to the gym and you work out for 20 minutes, the first 10 minutes you burned off carbs, but you did manage to burn off 10 minutes worth of fats in the second part of the workout there, right? So this is where these high protein diets come in. Things like the Atkins diet was one of the first big famous ones, South Beach diet. These generic, there's different ones, low carb diets. So we drop carbohydrate energy down, which means we have to consume more proteins and more other, salads and that kind of mess. But we drop our glycogen energy low so that we can quickly burn off carb energy and start burning fat. And that's designed to help lose weight as we're burning more fat. Now, when it comes to diet, understand it's very difficult to lose weight just by dieting. It's very difficult to lose weight just by working out and eating unhealthy. The best strategy is to, again, eat in a healthy way and increase your activity levels. That's the most optimal, most healthy way to lose weight if that's your goal. So the idea of carbohydrates and their role in energetics. There are some other carbs. I'm not going to spend too much time with these, but these are structural. These are the cellulose and chitin sort of molecules here. Cellulose being the type of carbohydrate that we find in plants, in lettuce, and that kind of stuff. Celery is a really good example. It's fiber, right? If you eat corn, right, you can digest the starch, but our body can't digest that little husk on the outside. That's fiber, right? We need it. We need it for our digestive system. It helps keep you from getting constipated, that kind of stuff. But that's the fiber that grandma and grandpa talk about, right? Cellulose. A cousin of cellulose is what we call chitin, right? This is not chitin, this is chitin, right? Chitin is a Greek term. It's a cousin of cellulose. It's the type of carbohydrate that we find around insects, little beetles. If you squash a bug, you hear that a little crunchy sound. That's the exoskeleton of these insects, right? It's not made of protein. It's actually a very rigid, very hard chitin. I don't know. I've never tried chocolate-covered crickets. I don't necessarily think I'm missing much, but if you were to eat chocolate-covered crickets, you would be able to digest the chocolate. You would be able to digest the inside parts of the cricket, but you would not be able to digest the shell of the cricket. If you eat shrimp, you don't digest that little shell, the exoskeleton, right? Because it is made up of chitin. If you went on an all-you-can-eat salad diet, you would be malnutrition very quickly because we do not have the ability to take energy from cellulose. It's too rigid. It does have energy, but our digestive system can't extract energy from that. In order to survive off of cellulose, you must be like a cow. You must be an animal adapted. And how are they adapted? They have not just one stomach like us. They have 1, 2, 3, and 4 stomachs. So the cow eats grass, which contains a lot of cellulose. They eat it. It goes all the way to the back. They ruminate it here. They digest it for a bit. And it gets moved up to stomach number 2. Different enzymes, different pH. And then they kind of burp it up. I don't know if that's ever happened to you. You burp into your mouth a little bit. Ew, it doesn't taste very good the second time. But they burp up their food. It goes back into their mouth. And they chew it some more. They literally chew up this food that they've been digesting already in 2 stomachs for multiple hours. Yeah. So they chew it some more. They re-swallow it. And it goes into stomach number 3. This blue line. Blue line, stomach number 3, stays there for a while. Then stomach number 4 stays there for a while. And eventually they move it, and then it passes out of their body. And if you've ever seen what comes out the back end of a cow, it looks like grass. It's very grassy, like just mulched up grass. So 4 stomachs, double chewing action, and it still looks like grass. It takes a lot of energy to extract, it takes a lot of work to extract energy from cellulose. For humans, we only have 1 stomach. We don't have double chewing action. So we can't really extract energy from that cellulose molecule. So I hope that makes sense a little bit. Let me backtrack to the oddball, right? So now we get into the oddball category of carbs. These are the oligosaccharides. I don't know how your family works, but normally there's an oddball in every family and just kind of, wow, they don't quite fit in very well. That's the oligosaccharides here. So oligosaccharides are saccharides. They're carbohydrates, but down here, they are not, I repeat, they are not used as an energy source. That's not their role. Their role is to mark the cells. They're going to be critical in cellular recognition, cellular marking. So for example, if we were to analyze your blood cell right now, your blood cell would have a couple of markers, right? It would have a couple of markers. One saying that that blood cell belongs to you. It's like a stamp. It's like a little name tag. This cell belongs to you, right? And it's got other markers that tell you that blood cell is a type A blood cell or type B blood cell. Right? And this is where we get that ABO blood system. So because of the little oligosaccharides that are on the external surface of these cells. So important. We need these cells to identify what we say self versus non-self, right? I don't know if your childhood worked like this. When I was a kid, we got a new jacket or we got a new notebook or something, right? The first thing we were given was a Sharpie. Here, put your name on the tag, right? Put the name on the tag. Put the name on the book, right? And that is a way to identify that object, that item belongs to me, to you particularly, right? So I was always losing my jacket. I had to go to Lost and Found. Okay, well, can you identify your jacket? Well, yes, but it's a black jacket and it's got JM on the tag. Okay, yeah, this is your jacket. So basically, by putting your name on there, you identify it as yours. So our immune system works this way. We have to put our own mark, our own stamp on our own cells. So the immune system will know, okay, this cell belongs here. Let me leave it alone. If a virus, a bacteria, something else comes in with a different cell marker, the immune system knows which cell to attack. And we have to have then the functionality of these oligosaccharides. This is what helps keeps us healthy, right? It helps keep our immune system functioning. If you have a dog at home, right, that dog must, well, it really should be able to know who's supposed to live there and who's a stranger. So that dog should not bite the kids that live at home. It should bite the stranger that's trying to break in at night, right? So that would be an appropriate distinction between self and non-self. In the military, if I'm a soldier, I need to know who's the bad guy, right? I don't want to be shooting my own members, right? You hear this sometimes, friendly fire, where members of the military shoot down their own plane, right? Their own nation's plane, that kind of stuff. So that's an incorrect recognition, right? They didn't recognize properly. In sports, in football, the white jersey kid trying to tackle the blue jersey kid, that's appropriate, right? Now, if the blue jersey kid's trying to tackle the blue jersey kid, then that's not an appropriate response. So the immune system must know what's supposed to be in the body and what's not supposed to be in the body. There are some conditions that don't work as they're supposed to. We do have some flaws. There's some sort of situations that we term as autoimmune diseases. These are not supposed to happen, but they do happen sometimes. Let's say the condition rheumatoid arthritis. So in arthritis, there's a mistaken identity. So for whatever reason, the own person's immune system starts to attack the joints of the body, right? So you can see it's going to attack all the joints. It malforms the joints. It damages, very painful, causes loss of function. And again, the bad guy is not a bacteria. The bad guy is not a virus. The bad guy is the own person's immune system. So autoimmune diseases. There's conditions like lupus, SLE, systemic lupus erythematosus, multiple sclerosis, some hyperthyroid, Crohn's disease, Hashimoto's thyroid condition. There's a lot of conditions where the bad guy is our own immune system. So there's a lot of research being done. Why does this happen? Why did the dog start to bite the kids here? In, what went wrong? Did the dog get messed up? Did the kids change? Did the kids become a threat? So there's a lot of things that we need to address specifically on these, and those are going to be for a different discussion when you get into your anatomy class later. All right, so this is just an introduction onto the carbohydrates, the oligosaccharides here, right? So with that, backtrack to the beginning, and that concludes our discussion on carbohydrates, right? So not, again, that complicated compared to other things we've covered, just different structural levels, mono, di, and polysaccharides used for energy, oligosaccharides, the oddball, used for cellular marking, right? So with that, I will conclude this discussion. I'll get this uploaded soon. And there has been a homework uploaded as well, so you can keep up with everything as best you can. And I'll be seeing you on the next lecture.